Hello there. We were discussing on equations of motion of multi-degree of freedom systems, and we shall continue with the same topic, which is equations of motion for last time when you looked at it, you saw that it became two single degree of freedom system problems, and you may well ask me, well, what's the big deal? Why don't we solve it as single degree of freedom, because it's just 2 degrees of freedom? Well, actually, today I'm going to take you up on a particular problem in which I will show that because of certain specific points that I tried to do in that system, we ultimately landed up getting uncoupled equations, and so therefore, we could make it into like 2 single degree of freedom problems. Okay. But what I am going to look at now is the same problem, the bar remains exactly the same, okay, except that now, so it's still not allowed to go in this direction. Okay. However, instead of a beam on elastic foundation, I have 2 discrete springs. Okay. And what I am going to do is, I am going to say that this is equal to k, and I am going to make this equal to 2k. Okay. This is still m bar, and the loading, well, I am going to say, well, it's going to be P 1 and P 2. Of course, please note that if these are not time dependent, then the whole problem is not time dependent. So, there is a the P 1 and P 2 are time dependent loads. So, this is the problem. Same problem, the same bar, excepting that I have discretized the load. Now, let's try to solve this problem. Okay. So, if I give it an arbitrary displacement, okay, and I still define my degrees of freedom at the geometric center as u x and u theta. So, they are the geometric center. Okay. And so, then if those are my u x and u theta, then any arbitrary displacement, displacement at any particular point can be written as xi 1 u x plus xi 2 u theta, and similarly u x is equal to, since xi, the shape functions are not functions of time, so it becomes this way, right. So, this was the basis that we used in the last lecture, and so if I use this, right. So, therefore, if I look at it, the inertial force. So, if I look at the forces on my structure, right, the forces on my structure are going to be the following. Here is going to be a net force, where the force is going to be equal to k into, now what is xi 1 at this particular point? It is going to be minus x by L. So, it is one into u x and then plus k into minus L over 2 u theta. Over here, this is going to be equal to 2k into 1 into u x minus plus L over 2 u theta, okay, u theta. So, what we have then, these are the two forces, then you have load P 1, load P 2, and on top of that you have these inertial forces, and the inertial force at any particular length at point x is going to be equal to m bar dx into xi 1 u x double dot plus xi 2 u theta double dot. This is inertia force on infinitesimal element. Okay? So, this is the inertial force on the infinitesimal element. So, now to solve for u x and u theta, we require two equations. So, for writing the two equations, the first equation becomes, I am going to give it xi 1 into del u x. That is the virtual displacement that I am going to see. Okay? And all I have to do for getting two equations is write down virtual work equations for two different independent, linearly independent. And since my degrees of freedom are independent, I always take displacements that are corresponding to the degree of freedom. I know that they are independent. Then I can get two independent equations. So, if I look at this, this is my xi 1. So, then what do I get? I get the following. The force P 1 undergoes 1 into del u x positive, P 2 into 1 into del u x. Then I have minus, because these are negative work, k into u x minus L by 2 u theta into 1 into delta u x. Okay. Then minus 2k into u x plus L by 2 u theta into 1 into del u x. That is also the kind of thing. Okay. Then I have the mass, and the mass is the following. It is m bar dx xi 1 u double dot x plus xi 2 u double dot. This is the force into xi 1 into delta u x. This integrated over the whole length, right. So, what do we get then? I am going to put these equal things together and put them in a proper format. And so, what I get then is I get the following. I get, see, I have already done m bar x xi 1 squared, I have already done that, right. So, what do I get? I get m bar L into u del plus 0 into u double dot theta, okay, the entire thing into del u x plus, now let us put the u x and u theta separately. So, I get k, so I get 3k u x, and then I get plus, and then I get minus. So, I get minus k L over 2 sorry, this is u x and this is u, sorry, there is no u theta into del u x is equal to P 1 plus P 2. So, in other words, finally, the equation becomes m bar and into del u x. Del u x is there everywhere. So, finally, we get this is the first equation that we get by putting the first this one. Right. So, this is the actually a work equation, but since delta u x goes out, it looks like a equilibrium equation. So, we have got the first equation and now what we need to do is we need to define another virtual displacement pattern which is not included in the other pattern. So, if you do this, okay, the obvious one to do is a virtual displacement pattern which is like this, and where this is minus L by 2, this is L by 2. So, if you give this pattern, then what does the virtual displacement virtual work equation look like? Let us start. The first one is that P1 here. So, P1 is being subjected to this plus P 2 into, right. Then we have plus K into, that's this force, right, and I am giving plus because it has minus L upon 2, right. So, it is actually minus into minus makes it plus, okay, L upon 2 u theta into L by 2 delta u theta. Then we have the other one. So, that one is being subjected to minus. So, it is minus. Okay, so, it is minus 2k into u x plus L by 2 theta into L by 2 delta u theta. Okay. And the final is the mass equation, and if you look at the mass equation, what you get is minus, now integrated over the whole length, m bar dx, that is the mass per unit length, into the acceleration, which is this, and so this multiplied by the, right. So, here you get xi 1 xi 2 integrated. We know that we have already evaluated this in the last equation. So, if I put that in, what do I get? I get the following: 0 u double dot u x plus m bar L cubed by 12 into, I am sorry, this is u d theta into del u theta. Then we have, now if you look at the other one, I am going to put the u x and u theta part together. So, from the u x, if you look at this, okay, k u x is this one, and on this side, and that is multiplied by L by 2. So, it is k L by 2 plus, and then here I have minus 2 k L by 2. So, I get I am going to put plus here, minus k L by 2 u x. Okay. So, that is the first one that we get. And then if you look at this, right, you have the other one, this one turns out to be minus k L squared upon 4, right, minus k L squared, and this one comes out to be minus 2k into L squared by 4. So, both of them are minus. So, you get minus k and then minus 2k both into L squared by 4. So, what you get is minus 3k into L squared by 4. So, that basically becomes what? It becomes equal to minus 3k 3 upon 4 k L squared. So, that is what I am going to put down here. One aspect that I need to look at very carefully, and that is that I need to put this part, if you look at it, minus k, all of them are on the same side. So, when I take this minus k and I take this k and minus k L over 2, I get k minus k L over 2. Okay. But if you look at this, this essentially becomes what? It essentially becomes, when I take it on the other side, I get it equal to, just like on this one, actually when I took it on the other side, if you look at this, right, this is plus k L squared and this is minus 2 k L, but this is on this side. When I take it on the other side, it becomes plus k L by 2. So, this is plus k L by 2 and this is plus k L by 2. And if I look at this one going back, this one again is on the other side. So, I need to put it, if I put it on the other side, I get it equal to plus k L by 2 and this one becomes 3k L squared by 4 u theta into del u theta is equal to, now if you look at this, this becomes on the, this is on this side, so it becomes P2 L by 2. So, it becomes minus P1 plus P2 into L by 2 into delta u theta. Since delta u theta exists everywhere, so finally what do I get? I get it equal to the following. I get m bar L cubed by 12 into u theta double dot plus k L by 2 u x plus 3k L squared by 4 u theta is equal to P1 plus P2 into L by 2. So, putting together, this is the second equation. So, putting together both equations together, I am going to rewrite both the equations together, and if I rewrite both the equations together, I get the following. I get it equal to m bar L u x k L by 2 u theta is equal to P1 plus P2, and the other one is m bar L cubed by 12 u theta plus k L by 2 u x plus 3k L squared upon 4 u theta and minus P1 plus P2 into L by 2. So, if I rewrite this in a equation in a matrix format, what I get is this: m bar L 0 0 m bar L cubed upon 12 equal to P1 plus P2, and on this one I have P1 plus P2 into L by 2. Okay. So, this is what we get on this particular equation. So, this is the mass matrix, this is the stiffness matrix, and this is the load vector. So, finally, what does it look like? Well, m into u double dot plus k into u is equal to p. And note this time that since you see this equation has u x and u theta, and this equation has u theta and u x. So, they are not uncoupled. They are not uncoupled, and since they are not uncoupled, it is actually two simultaneous differential equations, and that is why you have this. Okay, if m or k or both are not diagonal matrices, then automatically the system becomes coupled, and in this particular case m is equal to m bar L 0 0 m bar L by 12, k is 3k, kl by 2, kl by 2, 3k L squared upon 4, this is 3. Okay, so, that is k, and the p vector is equal to P1 plus P2 and minus P1 plus P2 into L by 2. Now, if you look at this, the mass matrix is a diagonal matrix. Why? Well, there is a reason. Because the center of the joint, if you remember, we defined the degrees of freedom here, which is also the center of mass. When you define equations at the center of mass, then the mass matrix always becomes uncoupled. However, the stiffness is no longer uncoupled because the lateral and the torsional degrees of freedom here, the lateral and the rotational degrees of freedom are coupled to each other for this particular case. For the case of the subgrade beam on elastic foundation, where k was a constant and m bar was a constant, you see you got uncoupled. Why? Because the center of stiffness. What is the center of stiffness? The center of stiffness is when you apply a static displacement, the net force goes through the center of stiffness. So, if you looked at it, the center of stiffness, if you had it uniform, when we had uniform over the entire thing, the center of stiffness was at the center of mass, and if the center of mass and the center of stiffness are at the geometric center where I have defined my degrees of freedom, I have uncoupled. But since in this particular case, since this is k and this is 2k, understand that where is the center of stiffness? Well, if you really look at it, the center of stiffness is somewhere over here, 2/3 from this and 1/3 from this. That is the force, that is the net force due to these two unbalanced forces. So, since the center of stiffness is here, okay, so therefore, since the degrees of freedom are defined here and it does not coincide with the center of stiffness, what we land up getting is that the stiffness matrix is coupled. Okay. Now, note something very interesting, and that is that what is this term? M bar L. M bar L is the mass of the rod. And what is this m bar L squared? This, if I say mass of rod is m, which is equal to m bar L, then this is actually m L squared by 12. Incidentally, this is the mass moment of inertia of this bar about its center of mass. So, this also has a specific, and that is known as the mass moment of inertia J. Okay. If you look at this, what does this represent? This actually represents that if I were to give it only a uniform, these k plus 2k would add up, and this is what you have here. Okay. Whereas, if this is the center of stiffness, which is the net stiffness is 3, and this distance, if you look at it, is L upon 6, 3 k into L upon 6 is k L upon 2. That is what you get. And again, since this becomes 2 k into L upon 2 plus k. So, this is like the rotational stiffness. So, this is the coupling term, and this is the rotational stiffness due to these two about the center of mass. So, these have all physical, and if you look at P 1 upon P 2, like what does this P 1 plus P 2? If I look at P 1 and P 2, and if I have the center, okay, P 1 plus P 2 is the load. And what is the net moment? Net moment would be what? P 2, see this one has negative, okay, this has positive. So, this is P 2 into L by 2 minus P 1 upon L by 2 is a net moment here. That is what we have. So, you see all of these terms have physical significance in the entire scope of this thing. And therefore, coming back to it, if we look at it, what do these define? If you look at this, this definition says that let us look at K 11. It is the load, the force corresponding to degree 1 if you apply a displacement equal to 1 corresponding to degree 1. So, if you look at this, what this becomes is the following. If I apply a displacement 1 at u1, which is ux, if I put 1, what do I get? I get force k and I get force 2k. So, what is the net force here? 3k. That is k 11. What is k 12? This is the force at 1 due to a displacement corresponding to 2. So, that means it is the force corresponding to this. If I give a unit rotation here, give it a unit rotation, this one becomes this way 2k L by 2. So, it becomes k L by 2, I mean sorry k L, and this one becomes which way? If it goes this way, this one goes this way. So, see this one is coming this way, this one is going this way, this is k L by 2, sorry k L, and this is k L by 2. So, what is the net force here? K L minus k L by 2. So, that is the force, that is k L by 2. So, you see it is a force corresponding to degree 1 due to a unit displacement corresponding to unit 2. What is k 21? K 21 is the force corresponding to degree 2. In this particular case, what is degree 2? Rotation. What is the force? Moment. So, it is the moment due to a unit displacement here. Let us look at the unit moment that we get here. You see, if I put a unit displacement here, what do I get over here? I get k L. What do I get? K L which way? This way. If I put displacement, what do I get over here? I get please note that what am I saying? This k 21 is the force corresponding to 2, which is the moment due to unit displacement 1. So, if I give unit displacement 1, that is this way, this becomes K L and this becomes 2 K L, sorry 2 K, 2 K and K, right. So, these are the things, these are the forces, which is why I had 3 K. So, let us look at the moment. Let us take moments about this point. What do I get? I get this way anticlockwise 2 K into L by 2, that is K L, and here this is counterclockwise K L by 2. So, that means the net clockwise moment applied is equal to K L by 2. So, that means the equivalent load over here is equal to K L by 2. Note, this is something very interesting, and similarly you can do 2 versus 2, there is no problem. Okay. Now, this becomes very important, and the important thing that becomes is that I can actually start looking at getting every thing very, very easily, and that is that these two are equal. Force corresponding to degree 2 due to a unit displacement at 1 is equal to the force at 1 due to a unit displacement at 2. Which law does this remind you of? This is the Maxwell-Betti law, which says what? Which is essentially says that force at 2 due to displacement at 1 is equal to the force at 1 due to displacement at 2. So, they have to be equal. So, these are always equal. In this particular case, they were K L by 2, K L by 2 in this particular case. Similarly, we can show that since this is also a force, mass into acceleration, that these also have to be equal to each other. Although strictly speaking, it is really mass into acceleration that makes it equal. Okay, but so they are also equal. So, in other words, both mass and stiffness matrix are symmetric matrices. This is a fundamental property of the mass and stiffness matrices. Now the point becomes, look, I have already developed the equations of motion. What do the equations of motion look like? Well, I saw that, didn't I? Mass was equal to this, stiffness was equal to this, corresponding to what? Corresponding to u x and u theta defined at the degrees of at the center point. Let me now try to look at a situation where I have the same problem, and I want to show you that this indeed, that the mass and stiffness matrices are indeed not property matrices, but they are property matrices corresponding to the degrees of freedom. This is a very important point to be noted, and the way I will do it is by solving the same problem by defining degrees of freedom somewhere else. As long as I understand that this is a 2 degree of freedom problem, I then say this, that look, I have the same 1, 2k, k, p1, p2, right? And now instead of, and this of course is m bar, okay, uniform. Now instead of defining degrees of freedom at the center u x and u theta, I will define u1 and u2. These are my 2 degrees of freedom. Note that it can't move in this direction. How is this different? Well, you see, when I put u1 equal to 1 and u2 equal to 0, what kind of a displacement pattern do I get? I get u1 equal to 1, u2 equal to 0. This is the displacement pattern. This is my xi1. Okay? And when I put u1 equal to 0 and u2 equal to 1. This becomes 1, 1. This is my xi2. You see, as soon as I have defined my degrees of freedom very differently, my xi1 and xi2 become very, very different. And so, when xi1 and xi2 become very, very different, what happens? Well, I'm not going to waste too much of time on getting this. Okay, all I'm going to do is, what's my xi1? Okay, I'm now going to define my x not from the center as I had done the last time. I'm going to define my x from here. So, if I define my x from here, okay, xi1 is equal to 1 minus x upon L, and xi2 is equal to x by L. Okay. So, now I know my m bar, my m11. What was it? M11 is due to the thing, and we saw that if you look at it, this is equal to 0 by L m bar xi1 squared dx. That's M11. Look back. I've already derived it. Look back and you will see that M11 ux in the first equation, if you look at it, was m bar xi1 x squared. Okay. And if I look at this, okay, this is going to be equal. And then if I look at M12 and M21, look at them. It's going to be 0 to L m bar xi1 xi2 dx, and M22 is equal to 0 to L m bar xi2 squared dx. So, now given these facts, let us find out what M11 and M11 is equal to 0 to L. I can put m bar outside, and inside I get 1 minus x upon L the whole squared. Okay. That is what 1 minus x upon L the whole squared. So, how do I get that? Then, if I can do this, derive this, m bar 0 to L 1 minus 2x by L plus x upon L squared dx. So, this is equal to m bar. So, this is going to be equal to what? 1. So, that is going to be equal to 0 to L. This is going to be x. This is going to be x squared upon L, and this is going to be x cubed upon 3L squared. Okay, 0 to L, all of them have 0. So, the other one has L. So, this becomes m bar L minus this becomes x squared. So, this becomes L, and here I get L cubed upon 3L squared. So, this becomes what? L upon 3. So, I get my equation to be m bar L upon 3. Okay. Do M22, which is m bar 0 to L x upon L the whole square dx, and you will see that this is also equal to m bar L upon 3. Let us derive m bar 12 and 21. Both of them are the same. M bar 12, which is equal to m bar 21, is equal to m bar outside 0 to L x by L xi1 and xi2, right, minus x by L dx. So, this becomes m bar 0 to L x by L minus x squared upon L squared dx. So, this is equal to m bar 0 to L x squared upon 2L minus x cubed upon 3L squared. So, this basically becomes m bar L upon 2 minus L upon 3. So, this basically becomes m bar L upon 6. So, if you look at my mass matrix, my mass matrix for this thing looks like m bar L by 3, m bar L by 6, m bar L by 6, m bar L by 3. Completely different from the previous mass matrix, isn't it? And so therefore, the mass is, so I have proved that the mass matrix is indeed this thing. And then let us look at the following, and that is, let us get the k. Now, for k, let us look back. What are the things that I require for k? So, let us look at that, and that is that if you look at this one, right. So, if I do, what's my loads? If I have a random thing, it's going to be equal to, so my k11 is going to be equal to load this and this, virtual displacement this too. So, k11 is going to be k here, if you look at it, it's going to be equal to k into 1 squared plus 2k into 0 squared. Okay, so that is equal to k. k12, which is equal to k21, is equal to this is the real one. So, this is going to be k into 1, okay, into what? Let us look at this, into this. So, this is going to be 0 plus 2k into this, which is 0, into this, which is 1. So, what is k12? 0. And k22? Well, it is going to be equal to k into 0, 0 squared plus 2k into 1 squared. So, that is equal to 2k. So, what does the stiffness matrix look like? If you look at this, the stiffness matrix looks like k is equal to k 0, 0 to k. Interesting, isn't it? The previous one had the mass matrix uncoupled and the stiffness matrix coupled, and here the mass matrix and stiffness matrix are uncoupled. And if I look at the p vector, well, I multiply each one. So, in one I get p1 into 1 plus p2 into 0. So, that is p1, and the other one I get p1 into 0 plus p2 into 1. So, this is my p matrix. Okay. And obviously, my u's in this particular case are u1 and u2. So, the mass, stiffness and load vector are completely dependent on how I have defined my degree of freedom. When I defined it at the center of geometric center with ux and u theta, I got m bar L cubed by 12, 0, 0, and I got what? What did I get here? 3k, kl by 2, kl by 2, 3k L squared by 4, and p's were p1 plus p2, and the other one was p1 L by minus p1 L by 2 plus p2 L by 2, completely different. But what does that mean? Does that mean that these are two completely different equations of motion? Well, later on I will show, we will come back to these problems, and I will show you that indeed, again, we have used two different degrees of freedom, independent degree of freedom set. They seem to look like generating completely different equations of motion. So, therefore, the mass matrix, the stiffness matrix and the load vector are property matrices, but they are not invariants. They are corresponding to the degree of freedom. And but does the degree of freedom define different things? We will see later on when I solve multi-degree of freedom problems, dynamic problems. I will show you, and we will come back to this problem to show you that no, this is not, they do not give me different solutions. Only thing is that I will get u x t and u theta t from that previous equation. In this one, I will get u 1 t and u 2 of t, okay, and they will not be identical. How can they? They are two different degrees of freedom. But you know, you look at u 1, what is u 1 equal to in terms of u x and u theta? U 1 is equal to u x minus L by 2 u theta, and u 2 is equal to u x plus L by 2 u theta. If you incorporate that and you put them in, you will see u 1 and u 2 are exactly the same, whether we use u x and u theta as my degrees of freedom, or whether I use my u 1 and u 2 as my degrees of freedom. That is what matters. Okay? So, overall what we have seen is that we have seen that ultimately a multi-degree of freedom, and now I am going to define this in a fundamental sense, a multi-degree of freedom and n degree of freedom. Suppose I have an n degree of freedom structure. It is defined by a displacement vector. Now, note the displacement vector last time when I defined u x and u theta, that was a degree of freedom displacement vector, but only thing is that u theta was a rotational displacement. You see, so it does not matter what I define. So, u 2 u n degrees of freedom. Okay. So, I need to define all these, I need to find out all these displacements to be able to define the displacement of the structure. Okay. And then I have f I vector plus f s vector is equal to the outside vector, and so that this one is equal to m into u double dot plus k into u is equal to p. Of course, note that I have not defined damping. Well, as I said that m and k are property matrices, damping is a completely different thing. We will see how we look at multi-degree of freedom problems. So, ultimately what we see is that this becomes our overall definition for a multi-degree of freedom system, and the entire problem then becomes nothing but defining the mass matrix. And all in mass matrix, all I need to do is find out m 1 m I j, and if I find out if m I j, each of them I have got the mass matrix k, I just need to find out k I j, and p I need to find out p I. These are once I find. So, the entire problem then becomes not for every complicated problem, I do not need to have to write down the entire equation, develop the equation. All I need to do is find out the elements of the mass matrix, the elements of the stiffness matrix, and the elements of the load vector. And if you look at this, what is this? This is the inertial force corresponding to displacement degree of freedom u I due to a unit displacement, I am sorry, unit acceleration. Okay. So, this is the force corresponding to degree of freedom I due to a unit acceleration corresponding to j. That is this. So, all we need to do is find out f at I due to unit. That is the whole problem. This one f s at I due to, sorry, no, there is nothing. This is displacement, unit displacement. And this, well, this is the load at I due to unit displacement I. So, this becomes this problem. So, ultimately this is what the problem boils down to, and once we find out each one of these, how do I find this out? Well, I give a unit axis. See, the whole thing becomes a very simple problem. The problem becomes give a unit acceleration, and how do I find out Fi? Well, give a virtual displacement corresponding to I and find out all the work done by the inertial force, and I've got it. Okay. Similarly, I can find this out by, how do I find this out? Well, give it a unit displacement, find out all the elastic forces, and then give a virtual displacement corresponding to I and find out the work done by all the spring forces, elastic forces, and that is your Kij. So, the entire, and what is Fi? Well, I give unit displacement corresponding to this and find out the work done, virtual displacement corresponding to this, and find out the work done by all the applied loads. If I do that, I am done. Okay. So, I have broken down the entire problem into small parts which can actually be solved, and next time onwards I am going to show you how this can be done for more complex structures. I started with a very simple structure to establish the fact, to establish 2 points. One, the fact that what is Mij, another fact that Maij is equal to Mji, Kij is equal to Kji. So, therefore, the mass and stiffness matrices are symmetric. Okay, that is one thing that we know. And second, that mass K and P are corresponding to degrees of freedom, they are not invariant matrices. Okay. So, this is very different from the previous one where M and K were property. Here these correspond to the degrees of freedom, and in this way they are very similar to the M star and K star and P star that we generated for the generalized single degree of freedom system. You see how we are slowly building up the blocks to come to it, and from here on out all I am going to do is find out Mij, Kij, Pi, and that is all. I have got my mass matrix, stiffness matrix, P matrix, and then I have got my equation of motion, which is given by mu double dot plus Ku is equal to P, and so I have got my differential equation which I will then solve. Thank you. See you next time. Bye bye.